Hello, my name is James Wei, and in this video, I just want to show you guys how to use LAMMPS and VMD to create simulations in molecular dynamics. So I'll just be creating a simple water and graphene system, and just show all these interactions between these molecules. So first, I want to open my VMD main window. And this is what you'll first see when you open up VMD. This is basically our display, and this is our main. You can see there's X, Y, and Z planes. So what I first want to get to is building our system. So in order to do that, I need to go to Extensions, Modeling, and Nanotube Builder to build our graphene sheets. Now this gives a bunch of options. What I want to do is build graphene, so I just go to this graphene sheet building option. I'll just make my graphene sheets 5 by 5 nanometers in length, and I'll create 5 sheets. And just click generate sheets, and VMD will automatically generate our graphene sheets. As you can see in our display here, I'll just make it a little bit bigger. So we just built our graphene sheets. It was pretty simple, and now we just want to add some water to it. So we just go to the same place in extensions and modeling, and we'll just go to add solvation box now. Now this screen is a bit different. Instead of just specifying the length and width of our graphene sheets, for water we need to specify the minimum X, Y, and Z coordinates and the maximum X, Y, and Z coordinates for a water box. So I'll just start the origin here, and in order to find out the maximum coordinates, we said that the graphene sheets was 5 by 5 nanometers in length. We actually have, or VMD actually has its coordinates in angstroms. So 1 nanometer equals 10 angstroms, so you have to multiply this by 10. So we'll make it 50 by 50 by 50 angstroms long. And I'll just click solvate here, and as you can see, once it takes a little bit more time because there's going to be more molecules. We just created water molecules, but we see that they're actually inside the graphene sheets. We don't really want that. We want our water molecules to be above the graphene sheets. So we can easily fix that. Just go to extensions and TK councils. And now in TK council you can write commands that'll basically edit the molecules you see on the display. So in order to move these molecules up, it's basically just setting a variable. We can set a variable called cell to select all the water molecules. We can see in our main window that the water molecules, they're under the name solvate.psf. They have molecule ID of 2. So back in our TK council, we just write atom select 2 and all. So what this basically does is that it sets this variable called cell. You can basically call it anything you want, to select all the molecules with the molecule ID 2, which is the solvate.psf. And we just want to move this selection by calling back our variable, that's the $, and typing in move by. We just want to move it up, so we don't want to move it like left or right. And that's our Z position. So we just want to let's move it up by 15 angstroms up. So as you can see, we have our water and graphene system done. It looks like all the water molecules are above the graphene sheets, and this is what we want. So we can save this file by first we need to merge these two moles. Since these are two separate molecules, because there's two IDs right now, we can merge these two systems together. And so in order to do that, we just right, topo tools merge moles and list the two molecule IDs, which is 0 and 2. So just press enter, and once this is done, we should see a molecule ID with our merged moles, and we have that here. So what we want to do now is basically write this to a data file, so LAMMPS will be able to read this. And in order to do that, we just write topo read or write LAMMPS data. And we can name this file anything we want. I'll just name it water graphene system. Oh, and a good thing to note is that before I do this, I really want to specify a folder to save this to, so we need to navigate this to a folder. So let's delete this for now, and we just need to navigate to a folder. I'll just navigate to my MD tutorial folder here on my desktop. So in order to do that, I just type cd. I navigate to my James folder and cd desktop and cmd tutorial. So now I'm in my MD tutorial folder, and now I can write my data file. So it will save in this MD tutorial folder once it's finished. So again, the command was topo write LAMMPS data, and anything, you can name it anything you want. I'll just call this water graphene system.data, and a VMD should be able to write this data file, and looks like it's done. So we can check our folder to see if it's actually there, and we can see that we do have a water graphene system.data. I can open up a notepad to show you guys what it looks like. So basically it has atoms, bonds, angles, dihedrals. We have 4,600 impropers right now, and in the LAMMPS file I'm going to show you in a few minutes, we actually don't code for these impropers. I'm just going to delete all these. I'm going to manually delete them. I mean, if you get more advanced, you can actually code VMD to make sure that no impropers are actually built, so you don't have to do this manually. But I'll just make sure there are 0 impropers. I just find impropers here, all the impropers. So I'll just delete all these impropers manually. Delete, and I'll save this data file again. So now let's go into LAMMPS to see how their code works. I had this code thankfully supplied by me by my advisor, Mr. Tom Zhao, and basically this code just codes for the units, dimensions, and all these interactions between the molecules in our system. So I mean, you can search what all these commands mean on the LAMMPS website. Basically, I'll just show you how to use this code and implement it in VMD. So first, we want to open up our command prompt by typing in cmd, and basically you see a similar thing. We navigate to our MD tutorial folder again. So I'll just type in cd desktop cd md tutorial. Yep, and now we navigated to our MD tutorial folder where we have this input file from LAMMPS. And in order to run this program, we need to type in LMP serial. I'm on a serial computer right now. -in, which is the type of file, and the file name in.cmt. Oh, before we do this, we actually need to change this to no, I was about to say we're going to change this data file but luckily it's all already been changed to read our data file that we set. It's called the water graphene system.data. So I'll just press enter right now, and this program will run for we set it to 5,000 time steps here. So it'll take a while. I'll just close it right now and open up what we get in what we should get after all this is running. So basically what this does is that it will create a DCD file which basically uploads all the coordinates and all the new coordinates and velocities of all the atoms so in the DCD file. So basically it will display our animation. I did this previously in another folder called Northwestern, so I need to navigate back to that folder right now in VMD. So CD Northwestern. So now I'm back to my Northwestern folder. If I not this folder. If I go into my Northwestern folder, it will create a DCD file for you. What we want to, since we have this DCD file, we need a PSF file to go along with it. So we need to create a PSF file from that basically is our system in the beginning. So we need to load back this data file that we made. So we have to go back to our folder, actually back to MD tutorial. Whoops. So sorry about that. So I'll just go back to our MD tutorial folder. So I'm back to my MD tutorial folder. I'll load back in our data file. Instead of write LAMMPS data, we read LAMMPS data, and it will read our data file, and this is the data file we created. So back in our main, I'll just delete all these other molecules that I don't need. So in order to write a PSF file for the DCD file to read that goes along with the DCD file, I need to write animate write PSF, and let's call it water graphene system.psf. And again, this will save in our MD tutorial folder. If I open that up to show you guys, we have a water graphene system.psf. And this was a DCD file that we just generated for about 0 time steps. There shouldn't be anything in there. Oh, there is. But it shouldn't be that big. It's only 198 kilobytes. But so I'll just show you guys how to load this DCD and PSF files to show your animations. It's basically the last step. So I'll go back to my Northwestern folder. CD desktop, CD Northwestern. And in order to load this DCD and PSF files, I need to write mol load PSF. What did I name it? I named it water graphene close.psf, water graphene close.psf, and DCD water graphene 2.dcd. And as you can see, we loaded in our simulation. So basically, if I go back to my main, I'll just delete this molecule for now. And if I press this play button here, you can see that the water molecules are interacting with each other. Looks like it's not actually interacting with the graphene. That's interesting. But we can change the speed of this animation. We can change the representation of these molecules. I'll change it to VW, apply, and I'll just play it again for you guys. Basically, so now we have our animation, and looks like this concludes our tutorial. Looks like it's working fine. There were no errors. Um, so this is basically just how you would load, basically create a system on your own in VMD, and create your DCD file in LAMMPS, and then load it back into VMD to display your animation and simulation. So I hope this tutorial was helpful, and thank you for watching.